I will introduce the last speaker of our session. Oh, are you James Carpenter? Oh,
No. Okay.
he said you were gone. So, okay. So we do have James. James Carpenter is going to tell us about prospecting on the upcoming Luna 27.
No worries. So, be delighted to know that I am here. I'm here on behalf of the ESA Lunar Exploration Team. We're based at the ESA ESTEC in the Netherlands, and we're part of the Human Spaceflight and Operations Directorate. So, that'd be the equivalent of your HEOMD. So that should also give you some idea of the context of what I'm presenting. So I guess similar to the RP mission, which you're probably all very aware of, this is something which is prepared very much in the context of future exploration and addressing knowledge gaps for exploration and technologies for future exploration. But I think there's a lot of good science that can also come out of this, and so we're looking to get good science and good technology and prepare for the future all at once. So within ESA, there's a kind of a core team of us in ESA, and on Prospect, there's kind of a few of us working on that. But then most of the work, really, I guess the technical work is being done by partners in academia and in industry. So with a company called Celex, based in Italy, and the Open University in the UK, who are at the moment leading a lot of the work on this. The rendering here actually is the David Page's map of where you might expect to find water based on temperature at the lunar poles. It's a rendering which we produced for a movie, which maybe I'll try and show you tomorrow, try and explain the context for lunar exploration in ESA and our vision for it. And so I'll talk a bit more about that tomorrow, and the way that the Russian missions, of which Luna 27 is one, fit into that. So Prospect is a package. We're planning for a Russian mission, Luna 27. It's one of a number of missions that Russia are preparing, and just one of the pieces in how we're looking to do lunar exploration through international partnerships. So this is Luna 27. It's a Russian lander. It's a Russian platform being prepared for a mission to the moon in 2020. I mean, it's a lunar south polar location. And Prospect consists of two parts. There's a drill, which we call Proceed, and Prosper, which is a laboratory. Now, the drill we're building on heritage from the Rosetta mission, so there's a European drill on the Philae lander on the surface of the comet at the moment. It's been operated on the comet. The indications are that it hasn't actually made contact with the surface because of the orientation of the lander, but it goes in and out just fine. And the laboratory is kind of a combination of an instrument called Ptolemy, which is on the surface of the comet at the moment, and a gas analysis package, which was on the Beagle 2 Mars mission, which we didn't get any data back, but we know it's there now because we found it very recently on the surface. And so what we're looking to do with this is to address exploration-related questions related to volatiles. So I'm not going to talk too much about what we might expect to find there, because I think previous talks have covered that fairly well, but rather to talk about how we would propose to try and do it with these particular instruments. So the questions we want to ask are lunar volatiles and regolith a potential resource for future exploration? So it's the same kind of question that RP is trying to answer. And then as a kind of a subtext we don't talk about too much, is what can resource-orientated measurements tell us that's a fundamental scientific value? And there's a huge scientific resource to be had from these volatiles. So in general, we want to find what's there, how much is there, what does it take to release the resource-relevant species, what are the sources of those volatiles, and what were the processes that put them there, and what can we use of this knowledge to understand the broader distribution. Now, this is of particular importance for us, because something you'll notice about the Luna 27 mission is it's a stationary lander. So we don't have mobility. So we have to pull as much information as we can out of whatever's right beneath us, and so we think for that, for example, very, very detailed isotopic measurements are a key thing for us to understand the processes of the volatiles that we find. So this is kind of a schematic view of the package and what it will do. So we have a drill which goes down to 2 meters into the surface. So this is a depth which we think is meaningful in terms of understanding and providing ground truth for some of the orbital measurements from neutron spectrometers, but also even going a little bit deeper to find out what's below. Then we have to access and take samples of potentially volatile rich material, and to take those samples and extract them whilst preserving them, and transferring them to the analysis which we performed in the laboratory. Now this is the really tricky part. So if we take regolith and we start adding water ice to it, the hardness of this material can become extreme very, very quickly. So if we get to saturation, it's like drilling into reinforced concrete. And so we have to do that whilst not putting too much energy into that material, so we don't heat it up, so we don't lose those volatiles. Then we have to hold that stuff, contain it, and transfer it, again without heating up and losing the volatiles that we want to measure. So this pushes us to try and find a very, very efficient drilling solution and to handle and move those potentially volatile-rich regolith in a very controlled way. So we then transfer that into some ovens, which are then sealed and transferred into the laboratory. These samples are then heated, reactants get introduced to the samples too, and the chemistry that comes off is analysed. So we have a concept for the drill. So at the moment, if you saw Chris Sackney's talk yesterday, he gave a really good overview of the different kinds of drilling solutions that you might employ in an environment like this. Now, some parts of the solution we've come up with are a little bit different, and that's partly because of the heritage that we have. So if we take the ExoMars drill, which is kind of our starting point, the ExoMars drill, it goes down to 2 meters, and it has it's purely a rotary drill. Now, if you want to have a really, really efficient drill, then you could use a hammer function. So we've taken the rotary drill from the ExoMars, we've introduced a hammer function to that in our nominal concept to try and increase the efficiency of the drilling. Now that increases the mass of the drill, but we're trying to work out at the moment what really the benefits are of having this hammer function. The other benefit that we have is in ExoMars we have a very, very compressed system, a very, very small envelope. So we have a drill which is made of lots of strings, and the drill is actually assembled during the drilling process. And this is very, very complex. Fortunately, on the Luna 27 we have a much larger envelope, so we don't have to do this. We can have a single drill string of about 2 meters in length, and that does make life a lot easier. But it does mean with the hammer function, of course, that if you have a hammer at the top of this thing, then you have a large mass on the top of a long string, and that's also, for engineering reasons, going to be a bit problematic for the spacecraft because you need to attach it at the top. So there's a lot that needs to be done in terms of understanding what the optimum system would be for this particular mission, for this particular scenario. The other thing we've gone for is, and you can't see it, actually hasn't come up on the other side, but we have a number of different sampling concepts. So the way that we've traditionally done it on Rosetta and on ExoMars is to drill down to a depth and then take a discrete sample from that depth and extract it. So in this case, we'd be looking at drilling down to any given depth, taking a sample, which would be typically maybe a cubic centimeter or so in size, and extracting that and transferring it. So there's a few different ways that can be done, and it's largely driven by the sample size that you're trying to get, material properties. So we're currently trading off 3 different possible sample extraction techniques. One of which is the one used on Rosetta, one which is used on ExoMars, and a new kind of slightly more exotic concept which we're looking at, so it might be more applicable for lunar regolith. Now, something else we're also looking into incorporating into this drill are what we call in situ measurements. So in the ExoMars drill, the drill string actually includes an optical head which is embedded in the drill string with an aperture, so that during the drilling process, near infrared measurements are made during the drill as it's going to the subsurface. Now, we'd like to try and do the same thing here, so we're looking at the possibility of including an optical head and making near infrared measurements during the descent. This is actually traded off against having a rotary hammer function, because the hammering can be a problem for the optical fibers and the accommodation of the optical head. So there may be something that we can't do here, but that's something that we're looking into, is incorporating that. We'll be making temperature measurements during the drilling anyway, so we'll definitely have temperature measurements. But we're also looking at trying to make electrical permittivity measurements of the sample during the transfer, so that we can understand what the electrical permittivity and infer properties of the sample from that, but also to try and observe volatile phase changes in the sample during the transfer, so that we can understand what's happened to it. We have some testing and breadboarding activities that are starting at the moment. So on the right-hand side of the slide, you'll see a number of different drill bits and drill heads that are being investigated at the moment to try and work out what the most efficient drilling system would be. This is a sort of fairly simple test at the moment, done in atmosphere, but with cool regolith simulant, which includes water ice cooled down to sort of very, very low temperatures of 150 Kelvin or so. In the next few months, we're going to be starting to perform breadboard tests in the larger facility you see here, which is based, which is in Italy, the Chisas facility in Italy, in Padova. And here, this is a system which has been developed for ExoMars, so it goes down to Mars conditions, but it does allow us to do drilling into icy materials and icy regolith materials at very low temperatures. In the next 12 to 18 months, we're looking to develop a facility like the one which Chris Sackley showed you yesterday, where we'd be able to do measurements and drilling and full system tests under real lunar conditions. So then the samples are taken and they're introduced to the laboratory. So I'll try and introduce you to the laboratory as a schematic. So we have what we call a volatiles extraction system, a gas processing system, and a magnetic sector system. So samples introduced to the solid inlet system here are then heated, or reactants can be introduced. So we can introduce oxygen to provide to do combustion, or we can introduce hydrogen or fluorine to perform resource extraction demonstration methods. And then we can make sort of general broad analyses of the contents using an ion trap spectrometer here, or we can do a complex processing of the gases here to make them suitable for analysis in the magnetic sector. So we expect from this that for the we'll get M to Z measurements in the range of 10 to 300 for the ion trap spectrometer and about 2 to 150 for the magnetic sector. We should get water detection about ppm levels for regolith. We should also, and then a number of isotope measurements here for some various species of interest. We should also be able to make measurements if they're in high enough concentrations of noble gases and some other compounds. So this is the sort of general sort of CAD model of what the laboratory looks like at the moment. And for the solid inlet system here is based on the one that was developed for Beagle 2, but we'll be looking to update this here. Actually, a particular challenge is the sealing process and actually getting a good enough seal so that we don't have losses that can cause fractionation and affect the precise isotopic measurements. So that's something we're working on particularly hard at the moment. To give us some idea of the kind of thing we might expect to see, this is work that was performed at the Open University using their Finesse instrument. So we'll be developing real kind of equivalent lab-based instruments in the next sort of few months. But for the moment, this is a conventional lab system. So here we see, as we do the heating, we see a number of different species coming off at different mass numbers. And that's what we might see in the ion trap spectrometer. In the magnetic sector, we would expect to see something much higher precision for the isotopic measurements during the heating. And we think this is important to understand really the processes that put them there and define the sources of these things. So just to finish off, we have phase A activities going on for the Prestige drill led by Celex and for the Prosper laboratory led by the Open University. Phase B activities are in preparation now. We expect to kick those off before the end of 2015, and for the Phase B activities we'll really be integrating this into a single prospect package. This will include system design and development, a number of development models, test campaigns, field campaigns, and also the beginning of the activities of a user group, which would be the equivalent to a science team, but covers really both the sort of fundamental science, but also exploration users as well, and looking at how we can use that science to inform engineering, so engineering can be a customer of the science. We expect the Phase C and D activities to be confirmed for progression based on the budget for the funding round in 2016. And the Russians tell us that the flight for Luna 27 will be in 2020. And we are very interested in the RP mission in ways that we can find synergies with that, the way we can learn from each other, and the way we can partner with RP in making these very important measurements for the future of exploration. Thank you very much.
Thanks very much. Very interesting. So we have time for questions. We can eat into Carl's time since he tried to skip you.
Yeah, Larry Taylor, University of Tennessee. Yeah, James, it looks sort of like you've taken the Luna 24 framework for their lander and added on Beagle. Is that correct?
Okay, so I've lost my slides. But yeah, so what you see on the you're not far wrong. What you see on the for the spacecraft, there's a very distinctive feature of Russian landers, which is what they call structural tanking, where they take the tanks containing the fuel, and that becomes part of the structure. And it's a very, very efficient way of building a lander. And it's a very distinctive characteristic that you spot. So that's the same that's been done in the past. They have their own payload suite on board the lander, scientific payloads. But for the laboratory that we are using is very, very similar to the Beagle 2 package, yes.
What about, I remember a meeting one time when DLR said that they had a rover that they would like to put on, and it was only 20 kilos or something like that. Whatever happened to that idea?
So, in the frame of when ESA, we were working on our lunar lander, and because of various things that happened, that was cancelled. But DLR were working on a very small rover, which could have been used on that mission for the lunar lander. I guess there was some interest in whether that could be applicable to a mission like this, but there isn't a rover on the Luna 27 mission now. No.
Okay, so the only thing you're really going after then is the possibility of water at depth, because you've blown away the surface when you landed.
Right, so that's both terrible and good. So we're interested in depth, so the surface will be contaminated, and we can't get away from that. And so we have to go beneath the surface if we want to make measurements. But one of the benefits we can have from the surface is that we know that's going to be very contaminated. So if we can make measurements of the surface material, that can also help us to understand the contaminants so that we can see them later on in our other measurements. So it's a blessing and a curse.
One more quick one.
Ahmed Badr, student intern. I'm not familiar with drilling technology, but you mentioned efficiency a lot. So I just want to clarify, when you mention efficiency, are you talking about the amount of energy that you release into the substrate that you're drilling through, or is that the amount of mass that you remove per rotation, for example, for a rotating drill?
Okay, no, that's very good. Really talking about the energy that we put into the subsurface. So what we want to minimize the increase in temperature. So to give you some idea, for the tests that have been done using the existing rotary drill into icy regolith in the Mars chamber, my understanding is that they typically measure temperature increases during the drilling of about 40 degrees centigrade, which may be too much. So what we're interested in is, if we introduce this hammer function, it's a much more efficient way of drilling into hard materials. So how much can we reduce that temperature increase that we put into that subsurface? And is it worth the effort and all the problems that it gives us too?